Physics is me, you, and us. Why do we study it? How can we understand quantum mechanics, relativity, the Big Bang Theory, and our universe? All of this and more are discussed by Dr. Nassim Magdi at the YouTube channel Nassimtron.
So I think it's time to start our seminar. Hello, everyone. Thank you for joining us virtually today. Our guest speaker is Dr. Nassim Magdi. Dr. Nassim Magdi earned his bachelor's and master's degree in Egypt, and he completed his PhD at Stony Brook University in the USA. Currently, he is a researcher there. Also, he is on the Stanford's list of the world's top 2% scientists. Congratulations on that. And today, he is going to give us a talk on physics of Quark-Gluon Plasma. Dr. Magdi, thank you very much for being with us today. It's a great pleasure for the club to have you here, and you can start. The floor is yours.
Thank you so much. It's really my pleasure to be around, and thanks for the kind invitation. I think I can start sharing my screen.
Yes.
Okay, I think you can see the screen now.
Not yet.
Okay, I didn't forget to share. Yeah, I put in the full screen, but I didn't share. Okay, here we go.
Okay, we can see it now. Yeah, you can see.
Yep. Okay. So I'm very happy to be with you today. Actually, it's a very nice invitation, and the talk today will be very elementary. So I think it's going to be an introduction to the physics of what we call Quark-Gluon Plasma. And as you see in my first slide here, try to make an analogy between the universe evolution, how our universe evolved, and what we call Quark-Gluon Plasma evolution. And that's really important, actually. In some early papers of this field, maybe like about 2005, people was calling the Quark-Gluon Plasma evolution as a little bang. So we have the Big Bang as what's happening in the early universe up to now, and we have the little bang, which is the evolution that we can achieve experimentally in the accelerator and lab environment. And let me start as it to be like a story in beginning of what we're knowing. And I think maybe all of you and all physicists are familiar with this kind of schematic cartoon I'm having over here, that we have our early universe are totally unknown for us. We start speaking about physics processing happening after blank time or blank epoch, and then basically we start shaping our physics a little bit about the grand unified time when we have all four forces are together as one force. This is at least our current understanding, when we have gravitational force, nuclear strong force, nuclear weak force, and electromagnetism as one force at that time, and then they start to split based on like how the universe evolved. And without going too much into the what we call the Big Bang Theory or the lambda CBM model, basically in very early time, one of the very first forces to start act was the strong force. And that's because we have a very high energy, very high temperature, and then we start creating what we call the, you can call it the strong interacting medium. And that's what we are very interested about. So I will be focusing on the second picture over here, which represent the strong interacting medium or the strong interacting force. And carrying that forward, the way we understand this different force, how they work, or at least the main three work, not the gravity, is through the standard model. As many of us know, standard model is an effective model based on the quantum field theory that describe the matter in the universe or the interaction in the universe as we have interacting matter like quarks, leptons, and we have particles that carry that interaction, what we call bosons, and of course the most last discovered one was the Higgs boson. However, the interaction between those quarks, especially along with them force carrier, that's the gluons, is what I'm very interested about. Those what give us the strong force, and it is very early form and the early universe. And historically, describing that was really challenging. So in, I think, 60s or maybe before 60s, people were thinking, how can one describe the strong interacting force? And the imagination was too wild. We have people thinking like Gell-Mann putting the first model that think, okay, we might have mesons interacting together to give us something like baryons, and he had what called the famous sigma model. It's still usable up to now after some modification, but at that time we was not having the clear picture about how the Quark model worked, how the strong force worked, and that was very, very essential in that discussion. After that, there was even a long discussion about how gluons work, and do we have a strings among those quarks, pulling them back and forth. And that idea was introduced, I think, by Vinciano, that had been adopted later by the string theory groups. You might find some debates historically about that. But this is a little bit of history about the strong force. It was not easy to start a theory that can describe the strong force. However, it comes along and become one of the most strong theory we have right now, which is the quantum chromodynamics. Quantum chromodynamics is the theory that describes the strong force. Based on that, we have interactions between quarks, we have interaction between gluons, we have interactions between quarks and gluons, and we have this different scenarios of interaction. All of this are described by the quantum chromodynamics. And to achieve that, that was very challenging. How can one study that experimentally? How can we verify the idea of, for example, the quantum chromodynamics coupling is different from most of what we know about other energies. Like, if you take the electromagnetic force, as you increase the distance between the particles, the force get weaker, or the coupling constant will be weaker. But in strong force, as you try to increase the distance, the coupling constant could diverge, goes to like what we call asymptotic freedom. It diverges to very, very large number, and then it's become nearly impossible to separate those quarks and gluons. However, how can we verify the existence of quarks and gluons? Study the quantum chromodynamics in the lab, basically. And this where the idea of Quark-Gluon Plasma and the experimental achievements of Quark-Gluon Plasma come into the game. So basically, we can imagine the nuclear matter, the protons and neutrons, as what we can see on the screens over here. Each circle represents proton or quark, and then we have them confined, meaning that they are inside the proton and the quark and the neutron. One thing we can do over here, imagine it, is increasing the heat, basically heating over the medium, or increasing the pressure. We squeeze everything. And by doing both or one of them, we can achieve what we call the Quark-Gluon Plasma. So we remove the boundaries between them, and we get them from the confined case into the unconfined case, or the deconfined case. And basically what you can see over here, this is what we're going to call Quark-Gluon Plasma, or the deconfined quarks and gluons. And the way to achieve that experimentally is by getting two beams of heavy nuclei. We have nuclei with a very rich protons and neutrons, and then we collide them in a very high speed, almost like speed of light, but the energy is what's matter over here, very high energy that moves from about 0.2 TeV, tera electron volt, into like 2.6 or 5 TeV at the Large Hadron Collider. And then the expectation is that creation here will go under some different stages. Basically, after the collision, you will create what we call Quark-Gluon Plasma. This Quark-Gluon Plasma is a medium that will, with very high temperature, comparable, even what we call sometimes comparable to the early universe, and then it cools down, it evaporates basically, or emit lights and other particles, and it cools down, and it moves to what we call hadron gas. That's when you start having particles, not quarks and gluons, that created, and we start seeing those in detector. We're going to speak more about that, but this was the main idea. How can one achieve the Quark-Gluon Plasma and study the quantum chromodynamics in the lab? Carrying that forward, we'll learn through early days that we have what we call a phase transition. This Quark-Gluon Plasma phase transition, meaning that we have the hadrons over here, basically protons and neutrons for now. And we have the vertical line is presenting the temperature. The horizontal line will represent the pressure. In this case, what we call the chemical potential. Just since it's academic talk, chemical potential is the amount of energy required to add or remove particles into the medium if you deal with something like grand canonical in statistics. And since we have also some audience that they are not physicists, the main idea, imagine it like the phase diagram of the water. We have temperature and we have pressure, and as you increase one of them or both, you move from one phase of the water to the next phase. This is what's happening over here. We found if we increase temperature, we can go to from the hadronic phase to the quark-gluon plasma phase, and this at very high temperature, this is what we call where LHC work and what we call the early universe temperature. However, if you start lowering the temperature to move to the quark-gluon plasma, you need high temperature and pressure at the same time, and this where the lab I'm working at comes to the game. It's called relativistic heavy ion collider, RHIC, and basically it gives us all of this area. You will see over here that this line over here represents the phase diagram. Since the early days, people start to speculate what's gonna be the phase diagram of this particular matter. And as I said, this is a matter that was existing at the early universe, so it's really important to understand this, where we think everything in the universe starts with. And basically, we have here 3 stages. We have the what we call crossover. So the crossover, you have this transition, smooth transition happening. So if you look to something like the entropy density or something else, you will find basically like no jumps in the entropy or anything. However, you have the first order phase transition, which characterized as any other phase transition. You can see, sorry, my mouse still. So you can see in this one, if you look to the thermodynamic properties, you can see the feature of the first order. And we think it has been theoretically proposed, not experimentally confirmed yet, is that those two are linked with a second order phase transition, what we call critical endpoint, at which the two state of matter, hadrons and quark-gluon plasma, exist. And that's very unique. It's supposed to be a discovery that's not finally confirmed yet. Let's take a look, since this is one of the main important features of the quark-gluon plasma. We can take a look into more details on the phase diagram, and that's why everybody is trying to study that at different stages. Again, we have temperature, we have baryon chemical potential. This is like a pressure. And again, the main idea over here, you can see everyone's trying to understand first this phase transition. So probing the phase transition by itself was a big challenge experimentally that we achieved a lot of the goals for that. So we know where is the first order happening, where is the crossover happening, what we didn't discover yet, the second order phase transition point. And that's for many reasons. That could be a talk by itself, but imagine that this little point over here could be attractive or repulsive. So as you try to approach it, it could push you away or it could move you to the other side, could attract you to different sides. So it's by itself had a feature that could prevent us from discovering it experimentally, but we're trying. So as I said, here several experiments can be worked here. So if you are at high temperature, that's where the Large Hadron Collider work. If you are at relatively low temperature, you have what we call RHIC, relativistic heavy ion collision, and we try to cover all of this area over here. However, if you have a low temperature but high chemical potential, this is where FAIR at Germany comes to the game, and GSI, I think, and the experiment that called CBM, compressed baryonic matter, that comes to the game at low temperature and high chemical potential. We think that this part over here is only achievable in neutron star. This when you have the pressure is very, very high, and then this pressure is what causing the quark-gluon plasma to create. It's not the temperature, and that's such condition can be achieved in neutron star, and you can see a lot of papers speaking about the quark-gluon plasma creation in neutron stars. Okay, so up to now we spoke generally about the what can one do experimentally to achieve this matter, but in details what we're doing. Actually, we have two main accelerators right now, colliders, that exist on the left over here, we have the Large Hadron Collider at CERN, and here we have the Relativistic Heavy-Ion Collider at Brookhaven. This is the one I'm working on, which is about to turn into a totally new accelerator. But in general, we can see over here that this is, I'm just focusing a little bit on the RIC. It's easy to explain. So basically, we have an acceleration ring that's called the EGS. This was an old accelerator that had been used for the new facility. And we used to have a 4 interaction points: star, Brahms, Phobos, and Phoenix. Currently, or like several years back, Brahms and Phobos achieved them goals very early in the game. Star and Phoenix keep competing until, like, I think 3-4 years, and then Phoenix had been shut down. It's coming back this year as S-Phoenix, which is a totally new detector specialized in working on jets. But that's also a little bit more explanation that can one go through later. So in general, what we do, we inject the ions to the AGS to be pre-accelerated. Then we inject them to the ring. They split into 2 yellow and blue rings. They keep collide until we want to reach the luminosity and the energy we want, and then they being collided into the points is our star or S-Phoenix. That's the state currently. And then we collect those data by what we call detectors. Those are some of the detectors existing at the Large Hadron Collider. You have CMS, which mostly kilometers. You have Atlas, which is in design, it's contain a lot of kilometers too, but those two here was designed in particularly for high energy physics, sort of discovering the Higgs boson beyond the standard model physics. However, they're still doing a very good job in heavy ion collision when they detect and deal with the Quark-Gluon Plasma. So each of them, however, there was not designed originally for that. They have a full program on the heavy ion collision. ALICE is the different. ALICE is designed for heavy ion collision. It's a multi-purpose detector that can do a lot of physics related to heavy ion collision. Especially, it has a gas chamber in the middle that's allowed to detect most of those particles coming from the Quark-Gluon Plasma. LHCb is sort of what we call a fixed target mechanism that's also, it has a different reason for the high energy. However, for particular, it can also do a heavy ion collision or a Quark-Gluon Plasma search. As I said, at the Relativistic Heavy Ion Collider, we have 2 experiments. We have STAR and we have Phoenix. And the main idea over there that you could have a middle chamber of gas chamber to try to detect as many particles in the center of the collision as possible. And then you could have different layers of detectors in forward or in the azimuthal part over here. Those are huge, big machines. As you can see, I think this is the man size over here, very small compared to the machine itself. So it's very, very huge machine. If anybody gonna be visiting United States or CERN, I'm encouraging you to see some of those experiments. Okay, carrying that forward, let's now dive into the experimental details. What's happening when we run the experiment? We have a collision, so we have 2 nuclei. This one here nuclei, this another nuclei. Take gold nuclei is the one most famous one used. And basically the main idea over there, they look like a pancakes. They look like here like a 2 pies. Basically, it's like a disk. And why that's simple? That's because the relativistic motion. We accelerate them almost to very close to speed of light, so they get contracted. They have Lorentz contraction. They look like more or less like a disk. It's not like a sphere anymore. And then they collide with each other. We define something called impact parameter. That's the difference between the 2 centers of the nuclei. Of course, the word impact parameter is a field dependent. So if you're doing high energy physics like electron scattering, your impact parameter will be the distance between the collision point and the center of the nuclei. But here, because we collide 2 nuclei, the impact parameter is from the center of the first nuclei to the center of the second nuclei. But that's very important because this area that collide, we're going to call participant region. This is where the Quark-Gluon Plasma can create. And then we have a spectator. Those are particles that will not participate into the collision. And those give you most of the feature of the collision. Basically, if you have a small impact parameter, this means your colliding area is large. and the number of produced particle will be large. The system created, the Quark-Gluon Plasma system created, will be larger. Basically the number of participants, the number of the particle participated in the collision will be large. However, if you take the second case, when you have a large impact parameter, is vice versa, because the number of particles that are going to collide with each other is small. This means you have the number of collision is small, the system created is small, and the particle production is also small. So basically, based on the information we can collect, we can characterize the collision geometry, how it happens, how central it is, how peripheral it is. This is what we call central collision with small impact parameter. Peripheral is with large impact parameter. And that's very important in characterizing the physics that we're looking for. Because now imagine this is a simple cartoon to show you if we have peripheral collision, that's small area of interaction. You can see we have mostly an elliptic shape that sort of expanding. And this ellipticity gonna basically help you moving your initial shape into your final shape. It's like you have an explosion. And that explosion, like moving forward, will represent on the pressure gradient that you have in the center. So the pressure gradient created over here will carry out the expansion of this medium. And in central collision, and you can see it's mostly circular, so the pressure gradient will be small. And that's very important in studying what we call the feature of the Quark-Gluon Plasma. So what exactly the feature that we are interested in is called basically the collectivity of this of the particle created. And this comes from the correlation measurement. And here, as I put in it, you can have, I think maybe most of us remember bananas in pajamas. Basically, they are like, oh, twins. So if I try to measure the correlation between them, they will be very highly correlated with each other. That's because they're coming from the same source. This kind of correlation, of collective correlation, you will find it in the fish moving in the ocean or in the particle physics. It's a picture of from our accelerator. Of each line of those represent a track or represent a particle that's coming from the collision. So what we are trying to do is getting the correlation. Correlation is supposed to tell us about the medium itself. And the main simple picture you can imagine, if I have this initial shape being transformed into the final state, what I measure in the detector, then I had a medium that can carry this correlation. So the Quark-Gluon Plasma created is a medium that can carry this correlation. Basically, you can say a liquid, hydrodynamic-like medium. But if this initial shape is not transformed into the final state, I couldn't see it in the detector, that means basically the Quark-Gluon Plasma is like a gas. The correlation between its particles is too weak and it doesn't preserve the initial information. So it's about preserving this initial information. And basically you can have here a longitudinal expansion that's along the beam direction, because we collide them along the z-axis, and the transverse that's in the plane that's perpendicular to the z-axis, that's an xy plane. And what we are looking for is called anisotropic transverse flow. Why that's important? As I said, if you had here a system colliding with a very high energy, the pressure gradient will be too large. Basically, imagine that you put a that's why we said it's very close to the early universe. We have a high density of particles, high density of quark-gluons with a very high temperature. It tries to cool down. The only way to do that is by expanding. And this expansion means you have a pressure gradient. As you go here near to the center, you have more pressure than you can go to the edges of this ellipsoid over here. And this is what we try to measure, how this initial, very condensed and squeezed medium gonna be expanded. And this will be represented by what we call anisotropic flow. And I think most of us had been thinking about this, studying this. I'm here giving you just an overall picture of this anisotropic flow. So as I said, you have an initial shape like the XY over here, and this will be expanding with very high speed, but we see it in the momentum space. So it goes from anisotropy, meaning that a symmetric shape in the X and Y, in the frame of the colliding nuclei, into asymmetry in the momentum space in the detector phase. This is the detector space now. And the main idea there is the correlation between this initial picture and this final state picture, supposed to tell me about the information about the Quark-Gluon plasma. And let me see if it's coming over here. Yes, this might, we can go back to the previous slide, but this might help us a little bit. We had pressure gradient. We had the system with very high pressure that gonna be expand, and this expand gonna be propagating like a sound wave. And most of us studied that either in nuclear physics or in even any lab, any physics lab, the idea of attenuation. The main idea over there, if you have a medium and this medium is taking some of your intensity, is taking some of your amplitude, whatever this amplitude is, that's what we call attenuation. So the idea in Quark-Gluon plasma is very similar. We had an initial shape that we call A0. We have a final shape that's in the momentum space that we call EX. And the attenuation, the difference between A0 and EX, reflecting beta, which is the medium properties. So now, if based on measuring this information, if I have A0, if I have EX, if I know what's the X is, in this case, I can get beta, which will tell me about the properties of the Quark-Gluon plasma. So going back to this one over here, basically our initial shape called eccentricity. And this is what you see here, taking from different initial state model, that based on the collision, this collision is not very symmetric. You have basically, in gold, you have about, you can say a couple hundred nuclei hitting each other. So you can do a Fourier decomposition to this initial shape. That's what we call epsilon 1, epsilon 2. So basically you can have a dipole shape, or you can have an elliptic shape, you can have a triangular shape, square shape, and so on. And basically the idea over there that the sum of all of the shapes will give you this red area over here, or the pink part over here. This is very lumpy. But now we can get from the models, from the initial state models, the initial shape. And from the experiment, we can get the final shape, and the relation between them supposed to tell us about the properties of the Quark-Gluon plasma. So one thing we did is, this was my one of my studies that I did, is looking into the attenuation between initial and final state. And that could achieve, here is the formulas. This had been developed by me in my PhD when carried forward. So basically we have the final state harmonic, the final state shape. We have the initial state shape. They're proportional to each other by a factor that give you the medium properties. And this factor had to be exponential, as any other medium we have in any kind of field. Basically, if you look to the regular nuclear physics or stable state, you will find this equation. So we can just, and this n over here is the shape order. As we said, we can have different orders of the shape. Since our shape is too complicated, so we do it in order. We don't do the overall shape. So basically we have the Vn, final state shape, over the initial state shape, supposed to be proportional to beta n square, where beta carries the medium properties. So what are the medium properties that's carried in beta? Those are the eta over s, the shear viscosity over the entropy density. This is dimensionless quantities in our field that give you basically the shear viscosity, how viscous is your medium. And basically you have 1 over RT, and this is your medium size. R is the size, T is the temperature. So both give you the size, the overall size of the medium, which we can, if you follow what we call entropy ansatz, you can replace this RT by the how many particles you produce. Basically, if you have a small system, you have a small number of particles. If you have a large system, you have a large number of particles. Some little mass, you can end up into this equation that the initial to final state ratio proportional to the number of particles produced in this exercise or in this collision, and the slope supposed to give you the medium properties. And then the question, what can we learn from that? And I did that in several scenarios. One of them is looking into beam energy, meaning if you change the beam energy, if you change the energy of the collision, you remember back then when we have this kind of phase diagram picture, you're basically changing your position in this phase diagram. So a theoretical expectation tells you can get the eta over s as a function of beam energy. It will be non-monotonic, and that could be very important because if you remember, we said we can look into what you call the critical endpoint. This will be where you have a minimum in the eta over s. another exercise, and this was important to answer, you can collide different systems. And the question is, the properties of the Quark-Gluon plasma will depend on the system. Like if I collide gold or uranium could be deformed, by the way, so it could have an oblate shape like that, or could have like an what's called a quadratic deformation, or a symmetric system like copper-gold or copper-copper, or even a small system like deuterium-gold or proton-gold. If the collision here will be different, the properties of the medium will be different. Here I'm showing you the answer to the second question. The first question we published already several years back, but we found a non-monotonic interaction that might hint toward the criticality, but it's still a debatable point. So I will show you the answer to the second point, which we published in the BRL, Physics Review Letter. And this one was here the results. So basically we have on the y-axis the second order shape divided by the initial second order shape, and versus the number of particles produced to power minus 1/3. So this is represent this equation up there. So the first thing is that we get all systems are linear and collapsed on top of each other. Before I look to the slope, that just tells me that the linearity means that this equation here is working. So we had did a great job delivering the proper equation to describe the interaction. But more importantly, it answered the question. We see all systems moving from very large system to very small system are collapsing on top of each other. That means the Quark-Gluon plasma created in all of these systems within about, here we're speaking about 5% or 2% are same. So within our statistics, was able to make this clear conclusion, and that all of the systems creating the same properties of the Quark-Gluon plasma. And of course, you can take the slope and infer the shear viscosity at this particular energy for all of those systems. This was published in BRL. The second exercise we did was a huge exercise. I will maybe go through it briefly because I don't want to take too much time. But in general, called the chiral magnetic effect. And the main idea over there that you have here in Quark-Gluon plasma, you have a free quarks. So those quarks are charged, and not only charged, they also have left-right-handed symmetry, what we call the chiral symmetry. And the main idea also after the collision, these particles that doesn't contribute to the collision will create a very strong magnetic field. So this magnetic field is the strongest ever created in a lab. Way stronger than anything we can imagine. And the main idea over there, it makes a quark splitting into the chirality, left-handed and right-handed. And basically this never been discovered before. This was very essential that you have a QCD vacuum, what called non-zero topological charge, is what we call quarks. And then you have a magnetic field created. You create something called chirality imbalance. And if it is correct, you should see, if in the detector frame, you should see a difference between the positive particle and the negative particle. And that even could be used later in industry. It's a very unique feature. And to do that, the lab had to organize an entire experiment over here that we call the isobaric collision. So the background in this kind of measurement is too high. So the idea we come up with is to collide two nuclei, ruthenium and zirconium, that they have the same number of particles. So both of them had 96, proton and neutron, but the number of protons are different. This means the number of the magnetic field created in one of them will be larger than the other one. So basically in ruthenium, we're gonna have larger signal than zirconium, but both of them should expecting to have the same background. This was a 3-year work in the lab, a lot of money, a lot of people had been putting that to see if we can discover this. And basically we have this called blinding analysis. It's had been a lot of work for 3 years. As I said, we are here the analyzers. This is where we are, but we have different committees that had been coordinating with us for 3 years. And after 3 years of effort, we come to the conclusion that we couldn't see it. That was a big discovery by itself. Still a lot of debate going on. But here, as you see, this was all, each point of those represent a group working. This was my point down up there. And the main idea over there, if we see thing above 1, that will be the discovery. And if we are below 1, that will be just, we don't see it in this exercise. And this was the conclusion. And before I end my talk, I will take just 2 minutes more, 3 minutes more. We are very interested about understanding the world around us and then how the matter created. And in the accelerator, we basically don't do that. We try to understand how the interaction happened, but we don't answer a lot of questions about the construction itself. It's basically like what's Richard Feynman, I think, was saying, the proton scattering is like hitting two Swiss watches together. You can say something about the building block of those two Swiss watches, but you will never tell how they work because you never looked into them individually. You're smashing them together, so you destroy both of them. You can tell an average information. However, what we are really interested about is slicing things down. And this over here, what we call deep inelastic scattering, that's the coming physics at the EIC, which is the electron ion collider coming in the United States. So what we're doing now in heavy ion collision, what we have in the watermelon up there, we're smashing the whole watermelon to see the red bars. But what we hope to do in the coming electron ion collider is to slice the watermelon. Not only that, we can dive deep into the watermelon, like you see over here. What we call deep inelastic scattering is basically scattering an electron from a proton or nuclei that will be very unique this time. And in this case, you can study the proton structure and the nuclear structure. There are a lot to be answered about the proton and the nuclear structure that's not answered yet. That's by itself another topic to be discussed in future, but let me tell you that now we are about 9 years away from the electron ion collider, the first electron ion collider in the world. That's going to be sort of the largest electron microscope to deal with the nuclei and the atom. I hope I didn't take too long, but thank you so much for being around, and stay tuned for the future of the nuclear particle physics. Thank you.
Dr. Magdi, thank you for the great talk. If anyone has a question, please feel free to ask.
Yes, maybe I have one question, Professor.
Okay, please.
Yes. So thank you very much. First of all, thank you very much for the great presentation. So I'm just curious about the experimental side of these studies. So did you obtain any, I don't know, for example, entanglement correlation until now between these quarks or not yet?
Okay, so that's a little complicated. I know that this was recent news by Atlas.
Yes.
Yeah, so what we in the Quark-Gluon Plasma, what you can do is looking into what we call entropy entanglement. It had been studied, not fully verified. So it had been a signature of that. So basically, you have different parts of the Quark-Gluon Plasma is entangled, and here you're not speaking about picture like that. You're not speaking about particle entangled with particle. You're speaking about regions entangled with another regions. It's way fascinating than just particle interaction or like entanglement. What we hope to study in the future EIC is the multi-state entanglement. So you can speak about not only two quarks, but how about three quarks? Because inside the baryon you can have three quarks entanglement. And that's maybe not everybody knows. When I speak usually about that, if you like use like three quarks, like yes, quark, like the entanglement in the picture of states, you can have 3 and 4 quarks entangled together based on what you're studying. So that's a part of the new accelerator hope is to provide a clear signature for the quantum entanglement in the quark state, in different quark states.
Okay, thank you very much. And you mentioned, I think that you mentioned that in the part of phase transition that you didn't until now also fix the second point or something like that?
Yes, so in this phase transition, we was able to identify the crossover range and the first order phase transition range. However, the signature for the second order is still debatable. So we think we see some signature experimentally, but it's not in, I will say, the community's debate whether can we call that a discovery or not, because this critical point is a little tricky. Some theoretical study will say, okay, you can have what you call an attractive. So every time you try to reach it, it pulls you away, it moves you down. Or it's a
Okay.
repulsive. So every time you try to reach it, it pushes you up. And this is, however, it's still interesting to study and it's still going. But I think we cannot confirm fully that we discovered this critical point. There are some discussions everywhere about that.
Okay. So thank you very much, and it's our pleasure, Professor. Thank you.
Okay, Professor Nassim, you
Yes.
hear me?
Yes.
Okay, thank you for this great talk. Just I have the same question as said by Khadija about the critical point. It's okay. What about the dark age? Because usually in our mind, because we don't have exactly what happened in this dark. And it means in this period. If you can give us some details.
You're speaking about the universe dark age.
Yes. Because
so I agree. So this kind of study is telling you how the particles should be created in this particular time. However, the answer will not be from this exact field. The answer will be from neutrinos physics. And now there are like several experiments in the nuclear particle physics exactly on the neutrino part, what you call, for example, double beta decay. And this, to answer one of the question about this early universe physics, is the neutrino the same as antineutrino or not? Like the antineutrino is the neutrino antiparticle or not? That's a big debate in the nuclear physics, and that could answer the idea why we have particles and antiparticle in our universe. That's still a question raised into the early universe. The other part is related also. This was a recent study, but it's theoretical up to now, is that these particles created in the problem with quarks, gluons, and all of that, they're gonna combine together to form atoms later, to form nuclei and atoms later. So you lose most of the information about these dark ages. But the unique part about neutrinos is that they don't interact much. They just gonna keep flying from these early days up to now. And there are like many suggested measurements that if it could be done at the neutrinos, you might answer, for example, how the gravitational field evolves with time from very early days in the universe to now. That's had been suggested, but that's a challenge in the experimental requirements, because in this case you need to measure a very low energy neutrinos, and that's not an easy. So like several questions to be answered in the near future. At least in the next 5 years, we hope to answer this question that's supposed to be related to the difference between matter and antimatter in the neutrino double beta decay experiment. That hopefully will be answered.
Thank you for the response. Thank you. Yes, because it's really yes, as you said, you should do it in the framework of the neutrino and not neutrino. It means that matter and antimatter. But really experimentally, I don't know how can do it.
The United States just approved 3 experiments to be run on what we call neutrino double beta decay. That's basically if the neutrino is the antiparticle for itself, and neutrinos are antiparticles. Those 3 experiments will be able to answer that question, and that's really essential for early universe physics. So that's being approved, and I think it will be done within the next 5 years.
Okay, thank you. Just with us, there is a master student.
Sure.
Can participate with us. For example, Ala, if you have questions, because you are interested in this field of theoretical. Ala, if you are here.
Yeah, I am here. I am attending, and I think that the main question I have is, how does this field sort of try to test our theoretical framework on like things like neutrino stars? Because I think that neutrino stars are using density to create the conditions we need to study the Quark-Gluon plasma, but is there any way we could replicate that in our laboratories?
Yes, that's what's happened in the experiment in Germany that called CBM, compressed baryonic matter. The idea over there is to have a low energy but very, very high density, and basically you can do that. So this part of course, you could not create the exact condition for neutron stars, but it's close enough that you have a very high density and relatively low temperature. So that experiments exist. I can maybe point you to some of the readings if you're interested. They also, they have a PhD program you might think about, but it exists in GSI in Germany. Yeah.
All right, that's cool. Thank you very much.
Sure. Good luck.
Any other question?
Yes, please. Okay, Dr. Nassim, you hear me?
Yes.
Okay, I search in the topic of Quark-Gluon Plasma. I see that this matter exists after just moment after the Big Bang. So my question is, it says before or after the symmetry, the spontaneous symmetry broken, because before the spontaneous symmetry broken, there is no mass. How we can define it? Something like a plasma. It's a massive particles. So this is my question.
Okay, so the word plasma over here is not coming from the relation to them. It has to be after the spontaneous symmetry breaking. Otherwise,
okay.
It will not
It's
create
after.
Yeah, but we call it for a different reason. I understand the word plasma is tricky. We call it plasma because it's the idea of being colored charged, and then it's not as a regular plasma. It's a plasma from the point of view that you have color, and those colors could be neutral, like protons and neutron colors, or neutral colors, or could be charged pulsing gluons.
Charged by colors. I know that's, but I find that exists after moment of the Big Bang, but the symmetry broken. I think it's after many years.
Let me think about it. When you say symmetry breaking, because the symmetry will be broken by the first by the first mass quark to be created. So basically, what you say over there, I can explain more. We have the main idea there is that they are too light. There are particular quarks that will be created very early, and those are very light. Speaking about up and down, it's really, really light. Those will not break the symmetry you still chiral symmetry. You still preserve the symmetry at that time with those particular particles. But once you go to the heavy nuclei, you're gonna break that symmetry. Chiral symmetry will be broken by definition. It has to be broken, and so it's a matter of what. Yeah.
Okay, thank you, Anas. Any other question? Okay, so since there are no more questions, and before we finish the seminar, I would like to ask you if you have any advice for those, including myself, who are starting their PhD journeys.
So I'll say, so there are a lot of opportunities, especially in the United States. There are the time every year that's all universities in the United States are open for PhD application. If you can get, now even the TOEFL is not a major requirement. They request what you call Duolingo, which is a relatively fine exam. Consider that because we have a lot of universities, speaking about thousands of universities in the United States. The chances of acceptance is not small at all. If you're interested in this field, we can really help you to get into the game. The new accelerator that will be built is in the next 30 to 35 years of physics in nuclear physics had to be done in that accelerator. That's the future of nuclear particle physics. So I don't hesitate to contact with anyone, plan your your movement early. The application in the United States starts about October, about those times. From every year, it ends by December. Some universities expand the application to January and February. So think about the application. If you're interested, let me know. I can give you some guidance. And in general, as you said, I come from Egypt, nothing different than you. It's basically very similar background in physics, very similar background in the lifestyle. So, and here I am, I can do it. So I think you can. Just don't hesitate.
Yeah, thank you.
Okay.
So thank you very much. And thanks to all the attendees. See you in another seminar. Thank you, Dr. Max.
Thanks for the kind invitation. See you.
Thank you. See you. Bye.
Thank you.
Thank you,
Thank
Dr.
you.
Max.
Everybody. Thank you
Thank
very
you.